Good morning, students. In today's lecture, we will discuss some exercises related to the theorem which we discussed yesterday. So our first problem is M1 and M2 are simple submodules of a left R module M such that M is the direct sum of M1 and M2. These M1 and M2 are not isomorphic. Then we are to prove that the ring of endomorphisms of module M over the ring R, that is isomorphic to the direct product of division rings D1 and D2. So first of all, let us restate the theorem that we discussed yesterday. There we had proved the theorem for n modules M1, M2, M3 up to Mn, and here we are having only two modules. So for n is equal to 2, let us restate that theorem. If M is the direct sum of modules M1 and M2, then the ring of endomorphisms of M over the ring R is isomorphic to the ring S. Here S is the ring of all 2 cross 2 order matrices having the entries of the form Fij, where Fij are the elements belonging to the set of homomorphisms from the module Mj into the modules Mis. So first of all, you will have to prove that theorem which we discussed yesterday. Now, in order to prove this problem, we will use Sker's lemma. According to Sker's lemma, if we have two R modules, M and N, and F is a non-zero homomorphism from M into N. If M is simple R module, then the homomorphism is 1, 1. And if N is simple R module, the homomorphism is on 2. And if M is simple R module, then the ring of endomorphisms of module M, that is a division ring. So let us use this lemma. To use this lemma, let us take an element from the set of homomorphisms from module M2 into the module M1. We have denoted this element by F12. If this homomorphism is a non-zero homomorphism, then because M2 is simple, so this non-zero homomorphism will be 1, 1. Also M1 is simple R module, so by Sker's lemma, this non-zero homomorphism will be on 2. Now this non-zero homomorphism is 1, 1 as well as on 2. And therefore, we can say that this mapping F12 is an isomorphism. It means M2 is isomorphic to M1 or M1 is isomorphic to M2. But this is a contradiction because we are given in the statement that M1 and M2 are not isomorphic to each other. So we can say that this arbitrary element which we have taken from this set, that will be 0. So we can say that the set of all the homomorphisms from module M2 into the module M1, that is 0. In the same way, we can prove that the set of all the homomorphisms from module M1 into the module M2, that will also be 0 because M1 and M2 are not isomorphic. Now, again, because M1 is simple R module, therefore, again by Sker's lemma, the ring of endomorphisms of M1 over the ring R, that is a division ring. And let us denote this division ring by D1. Also, the module M2, that is simple. So again we can use Sker's lemma. So by Sker's lemma, the ring of endomorphisms of module M2 over the ring R, that will be a division ring. So let us denote this division ring by D2. Now by the theorem which we discussed earlier, according to that theorem, the ring of endomorphisms of M over the ring R is isomorphic to the ring S of 2 cross 2 order matrices having the entries Fij. Now this S is of this form, and substituting the values here which we have obtained, so we can say that the ring of endomorphisms of M over the ring R is isomorphic to direct product of D1 and D2. Here D1 and D2 are division rings. So this completes the proof of this exercise. Now there is another exercise related to the same theorem. In this theorem, M1 and M2 are isomorphic simple modules. So the theorem is M1 and M2 are simple submodules of an R module M, such that M is the direct sum of M1 and M2. Here M1 and M2 are isomorphic. Then we are to prove that the ring of homomorphisms of module M into itself, means the ring of endomorphisms of M over the ring R. We are to prove that this is isomorphic to D2. D2 is 2 cross 2 matrix ring over a division ring. Now, to prove this, again, first of all, you will prove the theorem which I stated earlier. Now here, because we are given M1 and M2 are isomorphic, and also M1 is simple R module, so we can use Square's lemma. By Square's lemma, the ring of endomorphisms of module M1, that is a division ring. Let us denote this division ring by D. Now, because M is the direct sum of modules M1 and M2, and because M2 is isomorphic to M1, so this will be isomorphic to M1 direct sum M1. So we can say that the ring of endomorphisms of M will be isomorphic to the ring of endomorphisms of M1 direct sum M1. And by the theorem which we discussed earlier, according to that theorem, this will be isomorphic to the ring having the entries D, D, here also we have D. This is 2 cross 2 matrix ring over a division ring, and we have denoted it by D2. Thus we have proved that the ring of endomorphisms of M is isomorphic to 2 cross 2 matrix ring over a division ring. So this completes the proof of this exercise. Now our next problem is M is the sum of simple modules. M is summation Mi, and here each Mi, that is simple submodule of M. Also N we have taken as summation Nj. Here in this sum, all the Nj which we have taken, they are simple submodules of N, such that Mi is not isomorphic to Nj for any I belonging to the index set I and J belonging to the index set J. We are to prove that the ring of homomorphisms of module M into the module N over the ring R, this is 0. Let us prove this result by contradiction. Let us take F be a non-zero element from this ring. It means F is a non-zero homomorphism from module M into the module N. Now each Mi is a submodule of M, and each Mi is simple also. So we can say that F from each Mi into N, that will be a non-zero homomorphism of left R modules. Here these Mi are simple. Again we can use Square's lemma. According to Square's lemma, because Mi is simple, so this mapping is 1, 1. Also, the image of Mi under the mapping F, that will be contained in N, and therefore we can say that there will exist a suffix j belonging to the family of indexes which we have denoted by capital J, such that f of Mi will be isomorphic to Nj. Therefore we can say that f is an isomorphism from module Mi into Nj. But this is a contradiction, because we are given that Mi is not isomorphic to Nj for any I belonging to the index set I and j belonging to the index set j. So we get a contradiction. So this contradiction proves that our this assumption is wrong. So F will be zero homomorphism, and therefore we can say that the ring of homomorphisms of from module M into the module N over the ring R, that is 0. Now our next topic is ascending and descending chain conditions. So first of all, let us define what are ascending and descending chains of submodules of a module. First of all, we define ascending chain of submodules of a module. So let us take MB and R module and a collection denoted by the collection Mi. I belongs to the set of natural numbers. This is a collection of submodules of M. Then we say that this is an ascending sequence or ascending chain of submodules of M if each Mi is contained in Mi plus 1. This is true for every I which is greater than or equal to 1. Means M1 is contained in M2, M2 is contained in M3, and so on. So if this condition is satisfied, we say that the sequence is an ascending chain of submodules of M. In the same way, we can define the descending chain. So let us take MB and R module, the collection consisting of MIs. I is a natural number. This is a collection of submodules of M. We say that this is a descending chain if each Mi contains the module Mi plus 1. Means M1 contains M2, M2 contains M3, and so on. So if this condition is satisfied, this sequence is a descending sequence of submodules of M. Now, next we define ascending chain conditions. It is denoted by A.C.C. We discussed ascending chain of submodules of M. It means M1 is contained in M2, M2 is contained in M3, and so on. These MIs are submodules of an R module M. If this ascending chain of submodules of M becomes stationary after a finite number of steps, means if this chain is finite, then we say that this is ascending chain condition. Mathematically, we can say that if there exists a positive integer M such that the modules M and onwards corresponding to M, the module will be MM. Next module is M with M plus 1 in the base, and so on. All the modules starting from MM, they will be same. Means the chain which we have taken, ascending chain of some modules of M, that becomes stationary. Or we can say that each Mi is equal to Mk for every I which is greater than or equal to K. So this condition is called ascending chain condition. In the same way, we can define descending chain condition. In the descending chain condition, we have a descending chain of submodules of M. M is a left R module. So let us take M1, M2, M3 and so on. These are the submodules of an R module M. And we have descending chain. M1 contains M2, contains M3, contains M4 and so on. This is descending chain of submodules of M. If this chain becomes stationary after a finite number of steps, then it is called descending chain condition. Means we can say that each mi is equal to mk for every I which is greater than or equal to k.